Okay, hold on, yeah. Okay, could you please confirm if you can see the slides on the screen? All right, thank you very much. So today we're gonna continue with the end, the final part of energy gap, right? Energy gap lecture. So we stop at the discussion of conduction of carriers, where we compared the conduction of carriers in insulators, in conductors, and also in semiconductor. Okay, so let's just recap our previous discussion before we move on. Right, so we've discussed a little bit on the conduction of carriers in metals, where we have two cases, for example. The first case being the complete overlap between the valence band and conduction band, and then we have partially filled case, right? For a few examples of metals, and then for insulators, we have discussed that the energy gap is so large that the valence band electrons requires a massive amount of energy in order to be excited into the conduction band, right? And semiconductors, on the other hand, possess the intermediate properties because the band gap is not so big, but there's a distinct energy gap between the edge of conduction band and the edge of valence band, which forms the EG or forbidden gap. So we've also discussed that at T equals to 0 Kelvin, all electrons stay in the VB. So hold on, let me just approve some of your friends joining now. Right, at T equals 0 Kelvin, all electrons reside in the valence band, and there's no electrons in the CB. And semiconductors in this case are poor conductors at low temperatures. Okay. On the other hand, when the temperature rises gradually, for example, and if you say if you're assuming T equals to room temperature, so the valence band electrons possess a sufficient amount of energy in order to be excited from the valence band into conduction band. Okay, for example, you can relate this to if you're talking about crystalline silicon, then the EG, the gap between conduction band H and valence band H is about 1.12 electron volt. If you're talking about gallium arsenide, then we're talking about 1.42 electron volt. So at this point, when you're talking about room temperature, for example, the thermal energy KT, right? The thermal energy equals KT at room temperature. So K being the Boltzmann constant, and then T is the temperature of that conditions, in this case, room temperature. So in this condition, appreciable number of electrons are thermally excited from the valence band to conduction band, right? So T, say, about 300 Kelvin, for example. Let me approve your friends. Say T at 300 Kelvin. So there'll be appreciable number of valence band electrons that are thermally excited into the conduction band, right? Overcoming the EG or the band gap. Okay, so it's 1.12 for crystalline silicon, 1.42 for gallium arsenide. So since there are many states in the empty state in the conduction band, a small applied potential can easily move these electrons, resulting in moderate current. So typically, you can have a moderate level of conductivity if the carriers are thermally excited into the conduction band at this temperature. Right, EG, as we learned in this topic, EG, the band gap, is actually temperature dependent. Okay, EG is temperature dependent, so that means the EG is dependent on the operating temperature of that particular semiconductor material. Okay, so the temperature dependence of the energy band gap, or EG, has been experimentally determined in the previous work. So we're just here to learn on the observations found by the previous work. So you can see here that the EG, right, the EG is dependent to the temperature by this equation. Okay, and you can see the summary of EG of 3 different semiconductor materials. For example, germanium on the left, and then silicon in the middle, and gallium arsenide on the right. Okay, silicon, germanium, silicon, gallium arsenide, and then the factors affecting the equation, and you can graphically see the change of the EG, or the temperature dependence EG, to be accurate in the graph below. So here you can see the y-axis is the band gap of the semiconductor materials shown in the table: germanium, silicon, and gallium arsenide, ranging from T equals to 100 Kelvin up to 1000 Kelvin, right? On the right. Okay, so our temperature is somewhere there. If we're saying 300 Kelvin, for example. Okay, so you can see the inverse relationship between the band gap and the temperature as the temperature increases. And let's see the amount of change so that we can appreciate the dependency on the temperature. For example, if you pick silicon, you can see that at 300 Kelvin, silicon is about 1.12 there, right? 1.12 EV. And then when you increase the temperature to 400 Kelvin, you can see a slight drop in the band gap, 1.09 at 400. That's for, sorry, this is 500, sorry. 300 is here. Okay, 300 is here. So this is 500. Okay, so that's 300, that's about there. 1.1, 2, and then it goes down to 1.09 at 400, somewhere there. Okay, and it goes down to 1.06 at 500 Kelvin. 1.06 there. And then if you increase to 600 Kelvin, it goes down to 1.03, so just slightly. So you can see a small change in the band gap when you increase the temperature by about 100 Kelvin in step, right? Step by 100 Kelvin in increasing temperature. And you can see the dependency for gallium arsenide and germanium, right? So you can see the same relationship, but with a slightly different gradient. Okay, for gallium arsenide on the right and germanium on the left. Okay, so why like this? The EG of semiconductors tend to decrease as the temperature is increased. So it's the inverse. It is the inverse relationship between EG against T. Okay, EG against T. So roughly it's an inverse relationship, but the gradient really depends on the material. So the interatomic spacing increases when the amplitude of the atomic vibration increases. The atomic vibration increases due to increased thermal energy. So that means the fluctuation between the distance between the atom. So this effect is quantified by linear expansion of the thermal coefficient of the linear expansion coefficient of the material. Right, increased interatomic spacing decreases the potential seen by the electrons in the material, which in turn reduces the size of the EG. Okay, so increased interatomic spacing at high temperature decreases the potential seen by electrons. So that means it's a lot easier for them to overcome the gap. Okay, even though the magnitude is not so big, but you can see an inverse relationship between EG and temperature. On the other hand, the EG is also doping dependent. Okay, so that means if you change the doping level, right? So if you change the doping level, you should expect a change in the value of EG as well. So remember we learned last time the doping is the incorporation of foreign atoms or impurities in order to alter the conductivity of the semiconductor material. So for example, if you're talking about incorporation of group 3 or group 5, oops, okay, so group 3 being boron, aluminum, gallium, in order to make the silicon more p-type, and group 5 could either be phosphorus, antimony, arsenic, to make the silicon more n-type. Okay, so let's see. So the dependency of the EG on the doping is given by this relationship. Okay, EG, the change in EG is equal to negative 22.5, the square root of N, the doping level, divided by 10 to the 18 per centimeter cube milli electron volt. So the unit is like milli electron volt. So 1/1000 of electron volt, right? Small change. So let's see what happens graphically. So you can see the band gap change. So that means this is the delta EG, the change in the band gap. As you increase the doping level from 10 to the 16 towards 10 to the 20, right? 16 to 10 to 20. So from this expression, we can find that the EG shrinkage, or we call it as band gap narrowing effect, band gap narrowing, sometimes we say BGM, band gap narrowing effect, can typically be ignored for doping density less than 10 to the 18. So let's see, when you increase, say, you are here 10 to the 16, say you have 1E16 as your initial doping level, for example, and then and there is no band gap change, obviously, so it will just use the original value of the band gap. So if you increase the doping to 10 to the 17, do you see any significant change in the band gap on the Y when you increase the doping density or the doping concentration to 10 to the 17? Do you see any significant change on the y-axis? Anyone? From the graph? Not much, right? So that's little change. You can see little change, but then is not an appreciable change as far as the band gap is concerned. So it's very, very small. But when you go up to 10 to the 18, okay, when you increase doping level further to 10 to the 18, now you can see, if you're referring to silicon, the blue line, the blue curve, so you can see that the change in the band gap is that much, okay? So that's probably close to half of the 50 milli electron volt, right? 50 divided by 1000, that's like 0.05 EV. So that's a small change, but the change is there. It's more observable on the graph, right? It's more observable on the graph. So, but you don't see much before 10 to the 18. When you keep increasing the doping level to 10 to the 19, right, 10 to the 19, see what happens to the band gap change of the silicon. So now it increases to, say, about 75 or 80 milli electron volt, 0.075, 0.08 0.08 electron volt, if you convert that to electron volt instead of milli electron volt. So it's more obvious, right? If you compare to the original band gap. So that's that much of change, that much reduction, right? So you'll see more and more changes, or more and more reduction if you increase the doping level to beyond 18. Okay, so this is pretty much roughly the dependency of EG on the temperature and on the doping. So we're going to have a lot more discussion on this later on when we talk about extrinsic, the property of material in the device. Later on, you can see how changing your doping changes the properties of the devices, how changing your temperature changes the properties of the devices as well. Okay. So we have done with this part. Now I'm going to move on to the next topic. I've uploaded the lecture notes already on Elearn yesterday night. All right, so could you please confirm if you can see this slide on screen for me, energy and density of states, DOS?
Yes, doctor.
All right, thank you. So we're going to move on with Fermi energy and density of states as a continuation of from the previous topic, which is energy gap. So let's just recap as what I've explained last time. Typically, when we move on to the new topic, we're going to do some revision in the name of challenge what you have learned in the previous topic. Right, so let's move on to the first question. Define 1 electron volt. What is 1 electron volt? Anyone? You can unmute yourself. You can write down in the chat box as well. What is 1 electron volt? We've been discussing about 1 electron volt, 0 0.7, 1.1, 1.4, 3 point whatever. So what is 1 electron volt? Any volunteers? Alisa? Alisa, what is 1 electron volt? Alisa Sharafana. Alisa, would you like to share what's 1 electron volt? Alisa? Anyone else would like to share what is 1 electron volt? Okay. So we got here from Ravin and Hazik. Okay, Ravin says 1.6 times 10 to the minus 19 joule of energy. Yes, okay. But in terms of the definition, what does it mean? So that's the value, what I call, that's the corresponding value, if you like, in joule. Pato said energy equal to the work done on an electron accelerated through a potential difference of 1 volt. Okay, so yes, energy energy experienced or gained by an electron through a potential of 1 volt. Okay, so and the charge being 1.6 times 10 to the minus 19 coulomb times 1 volt potential, and that is 1 electron volt. Yes, so energy gained by 1 electron through 1 volt of potential, right? You have to be complete. So 1 electron through 1 volt potential gives you 1 electron volt. 1 electron times 1 volt. Right, so good. So let's move on to the second one. Define direct and indirect band gap semiconductor. Give example of materials for both categories. Right, so let's move on to direct band gap first. What is direct band gap semiconductor materials? Anyone? I give you a definition and then some examples of direct band gap. What are direct band gap semiconductor materials? What does it mean to have a direct band gap? Anyone? All right, page 1. Direct have same value of K in the energy band gap. So same value of K for what? What is having the same value of K? Let me see if there is another page. Have same value of K in the energy band gap. Okay, indirect have different value of K. Momentum. Okay, but then what do you miss here? Yes, it's about the value of K. You have the same value of K for direct band gap and different value of K between for indirect band gap. But then the value is referring to which curve? Which particular curve are you referring to? Which has similar or different values of K? Conduction band, and you have to be more specific. Right, conduction band and the valence band. To be more specific, the local minimum, the local minimum of your conduction band has the same value of K with the local maximum of valence band. Okay, and this is direct band gap, right? The minimum point, or you can say local minimum or local maximum, or minimum point or maximum point. Either one is fine, as long as you complete the definition, right? So, okay, so what are the examples of semiconductor materials with these properties? And examples of direct band gap semiconductors. Zinc oxide anymore? Had it coming? More? Zinc oxide anymore? Ada lagi direct band gap example. Silicon is not. Silicon is indirect band gap, right? We've discussed last time. Silicon is indirect band gap. But if you say amorphous silicon, yes. Amorphous silicon is direct band gap. But if you say crystalline silicon, it's indirect band gap. Yes, gallium nitride, gallium arsenide, titanium dioxide, yeah? Okay, patient. So that's why I mentioned last time, when we say silicon, we have to be a bit more careful depending on the context, because in this particular case, if we say silicon, it could either mean crystalline silicon, which is indirect, or amorphous silicon, which is direct, right? So you have to be a bit more careful with silicon, because it could mean either way, right? But on other materials, they are quite straightforward. All right, so let's move on to the next one. What is indirect band gap? So we've discussed a little bit just now. So they have different values of K between the local maximum and local minimum of CB and local maximum of VB, right? And how about the example material? The first one being crystalline silicon just now. Any other indirect band gap semiconductor materials that we have? Yeah, germanium, good, right? Silicon and germanium. Crystalline silicon, you can just write like this, crystalline, CSI, or this is the convention we use for crystalline silicon, and this is another convention we use for amorphous silicon, ASI, CSI, okay? So you can write either one. Typically you mentioned, you can write in full crystalline silicon or in full amorphous silicon. So if you talk about indirect band gap, you can say it's either crystalline silicon or germanium, right? So done. So the third one, how does temperature affect EG? So we just discussed 3 and 4. What sort of relationship are you expecting for temperature against EG against temperature? What sort of general relationship, right? Reciprocal relationship or inverse, or increasing temperature decreases the EG, right? Inverse relationship. How about the doping? How does doping affect EG? Okay, yes, Shazanani, EG will decrease when temperature increases. Good. How about doping now? How does the doping affect EG? What sort of relationship are you expecting from these two parameters? What happens when you increase the doping level, doping density, doping concentration? Sama. So we normally say doping concentration, doping level, doping density, carrier concentration. We use all of this interchangeably, right? So that means kadang-kadang kita pakai ini, kadang-kadang kita pakai another one, but they are actually referring to the very same thing. Okay, depends on type of dopant, but generally, how does doping affect EG? If you go for higher doping level, what happens to EG? Yeah, it decreases the EG. So, and you won't be seeing appreciable reduction of the band gap in the region of 10, 17 and above, 10, 18 and below, 10, 18 and below. You can only see at 10, 18 onwards, right? Before that, you can only see a small change in the band gap, delta EG, when you increase the doping level. All right. So in this topic, Fermi energy and DOS, density of states, we're going to cover a few things. The first thing is, what is Fermi energy? And then Fermi energy and semiconductors. Why is it important? So we're gonna look at the concept of DOS as well, density of states, I normally say DOS. Okay. And then probability of occupation. What is probability of occupation? And then finally, density of free holes or density of free electrons. Okay. So we're going to be talking on both free electrons and free holes. So let's go through the first one. What is Fermi energy? Right. This Fermi energy is given by a Fermi Dirac distribution function, right? The equation that governs this concept is called Fermi Dirac distribution function. Sorry. So when you say it's Fermi Dirac distribution function, so it will give you the probability. So it's about probability that a single energy state E will be occupied by a fermion, in this case electron, will be occupied by an electron at a particular temperature. So this is what Fermi Dirac distribution function is all about. So it will give you probability that a single energy state will be occupied by an electron at a particular temperature, right? Or at thermal equilibrium condition, right? And this Fermi Dirac distribution function is given by Fe. So Fe being the probability, and that is equal to 1 over 1 exponential of E minus EF. This E is the energy you are interested to know. What is the probability of the electron occupying that particular energy state, minus EF being the Fermi energy, over KT. KT is Boltzmann's constant times the specific temperature in that particular case, right? So this Fermi Dirac distribution function takes this shape. We're going to explore this shape very soon. So you can plot your energy on the y-axis. So just like the typical way do we do the plot, where you plot your VB, where you sketch your VB, and then up there is a CB, and then you are talking about electrons excited into the CB, and this drawing is also about energy on the y-axis, right? So that means if you're talking about the dimension of the plot on the left and the plot on the right, they are in the same dimensions, but they plot energy on the y-axis, right? And for Fermi Dirac distribution function, you will also see a probability, the Fe, being plotted on the x-axis. However, you will also see some conditions when the Fe is plotted on the y-axis and energy is plotted on the x-axis. You will also see that every now and then in different sources or references. Okay, but the principle is still the same. It's just that the way they plot is different. It's a lot easier to relate if you plot the energy on the y, because we have been sketching our VB and CB and the energy is on the y. So if you draw your Fermi Dirac distribution function with energy on the y-axis, it's a lot easier to correlate with the Venn diagram. Okay, so let's explore what is this. Right. So Fermi Dirac distribution function equals to 1 over 1 exponential of 1 plus exponential of E minus EF over KT, as said in the previous slides. So with Fe being the probability, yeah. So when we say it's a probability, what is the range of Fe that we are expecting in terms of its value, right? Okay, 0 to 1, isn't it? So good, 0 to 1, because we are talking about probability. So it can either be from 0 to 1. Okay, the maximum being 1 and the minimum being 0, because it's a probability for us to have that electron occupying that particular energy state at that particular temperature. Okay. So at absolute 0, when you talk about T equals 0 Kelvin, electrons will fill up all the energy states below EF. So nanti kita akan relate to the sketch. electrons will occupy all the energy states below EF, right? Below EF, called Fermi energy, with one and only one particle. They are constrained by the Pauli exclusion principle. At higher temperatures, some are elevated levels above EF. So at T equals 0 Kelvin, all the electrons will be occupying the lower energy states, and they are not excited into higher energy states for conduction. So they are all occupied in the lower energy states. So we're going to see how the temperature changes this. For low temperatures, those energy states below the EF have a probability of essentially 1. So that means when you have all the electrons occupying the low energy states at low temperatures, so the probability of finding electrons at that particular energy state is 1, because all the electrons are there. So you will find them there, right? So that means the Fe is equal to 1 when you are operating at low temperatures, right? So remember the Fe being probability of finding electron at that particular energy state at that particular temperature. In this condition, when you are operating at low temperatures, those above EF energy, Fermi energy, is essentially 0. So that means the probability of finding electrons at energy above EF will be 0, because there are no electrons over there at all. So the probability is 0, right? So let's have a look in terms of the graph. Okay, let's go back to the equation. So remember, the Fermi-Dirac distribution function is governed by this: Fe equals to 1 over 1 plus exponential E minus EF over KT. Don't get this wrong, right? Some student last time in the previous batches, it repeats every single batch. In every single batch, when the students wrote down this in the test or in the assignment, some of them got this EF and E wrong. Some got that like that, EF minus E. Okay, should be E minus EF. Okay, jangan silap. Kalau you silap nanti you buat calculation and then you're going to calculate wrongly and you're going to end up with wrong probability, wrong Fe. Okay. So now let's try to produce Fermi-Dirac distribution function from the equation. So let T equals to 0 Kelvin. So if you assume T is 0 Kelvin, what happens? So okay, in this case, this where I said is now where the plot is inverse. Now you see the Fe is on the Y and E is on the X. Okay, on the previous page you can see that here E is on the Y and Fe is on the X. So that means you can plot them either way. Ataupun kalau this particular graph, kalau you nak flip it 90 degrees anti-clockwise, you'll get the same thing anyway, right? You'll get the same thing anyway. It's just that the axis is inverse. Okay, so when E is less than EF, so when E is less than EF, where is it? When E is less than EF, where is this? E is less than EF. If you see on the x-axis, where is E less than EF? On the x-axis, where is the point where E is less than EF? Anyone? Is it on the right or on the left? On the x-axis. On the left, right? So remember, EF is in this case here. Okay, E less than EF means it is sitting on the left. So at this point, the exponential terms becomes 0. E is less than EF. This one becomes 0 and Fe equals to 1. Fe equals to 1. And you get that Fe equals to 1, right? So on the other hand, when your E is bigger than EF, you can see this like E is much less than EF, for example, for you to get a better picture. So on the other hand, when E is more than EF, the exponential terms becomes infinite. If the value in the bracket is very, very big, then it becomes infinite, and then 1 plus infinite is infinite, and 1 over infinite is 0, right? And therefore your Fe equals to 0. So then you get this Fe equals to 0 on the right. So that's why you end up with that square shape graph, right? So being Fe is 1 for the value of E less than EF, and Fe equals to 0 when E is more than EF. So this shows that for T equals to 0 Kelvin, electrons are at their lowest energy states, and therefore the probability of finding electrons at this temperature at energy higher than EF will be 0, because all the electrons are occupying the ground state. The probability of a quantum state being occupied is unity for E less than EF, which is there, and probability of a state being occupied is 0 for E more than EF there on the right. So all electrons have energy below, for me, energy at T equals 0 Kelvin. So remember, this is T equals to 0 Kelvin. So in this condition, all electrons have energy below Fermi energy. So all electrons have energy below the Fermi energy at T0. So that means they are occupying the states below EF. Okay, at T equals 0 Kelvin. So that's the main thing there. On the other hand, we're going to see later on the other hand, you will see when we increase the temperature, what do you expect when you increase the temperature? So this being the condition at T equals 0 Kelvin, can I explain more as to why exponential is 0? Right, if the value of E is very small, if you compare to EF, and then the exponential component will be very E less than EF, exponential term becomes 0. Yes, exponential term becomes 0, and then okay, let me just explain again. When E is less than EF, right, the exponential term becomes 0 here, and then exponential of 0, okay, 1 over 1 is 1, right? This becomes 0, and then 1 over 1 is 1. So that's why you get the probability of 1. So you can imagine this if you replace any value of E much lesser than EF, for you to imagine better, for you to get a better picture, right? So it'll probably be a bit tricky if the value is approaching EF, and but when the E is much lesser than the EF, then you can get a better approximation to this. Right. So when your EF is when the temperature is increasing, what do you expect to get? So remember last time, the original condition is like that. So you can either plot, say if you plot Fe on the Y and E on the X. So you're going to get this at T0 Kelvin. So what do you expect to get if you increase the temperature? What happens to electrons at higher temperature? When you increase T more than 0 Kelvin? Anyone? Will they get more energy or less energy? Electrons in the valence band? Okay. If you increase the temperature, the electrons in the VB will gain more and more energy, and then some of them will be thermally excited into the CB. Okay, some of them will be thermally excited. So that means when you increase the temperature, the probability of finding electrons at energy above EF is no longer 0, because some of them are already excited, and you will find some of them in the CB. So that means the probability of finding the electron as you increase the temperature will be higher and higher and higher, right? So at T0 Kelvin, Fe is a step function, so this is called a step function. However, when T is more than 0, the step smooth out or smoothen out. so that appreciable number of states below EF are empty and some states above EF are filled. So what does this mean? So this means when you have increasing temperature, T more than 0 Kelvin, so some of the electrons will be excited into the conduction band. So that means they will evacuate the ground states in order to be, as a result of them being excited into the higher states. So they will fill in the new states at higher energy and they will evacuate the states at the energy below EF. So that means some of the states in the lower energy will be empty and then some of the states at the higher energy will be filled as a result of the thermal excitations. So you will find higher probability of finding electron at E more than EF when the temperature is higher than 0 Kelvin, right? So when you say Fe is probability of finding an electron at that particular energy state at that particular temperature, you can also say that the probability of finding hole is the inverse, or 1 minus Fe. Okay, Fe is probability of finding electrons, so that therefore 1 minus Fe is probability of finding a hole. Okay, for example, if your Fe calculation, if your Fe calculation gives you 0.4, so what is the probability of finding a hole for this particular condition? Anyone? The probability of finding an electron at this particular energy state, at this particular temperature is 0.4. Yes, good. Therefore, the probability of finding a hole in the very same condition is exactly the inverse of the probability of finding electrons. So 1 minus Fe, in this case 1 minus 0.4, and that is equal to 0.6. Okay, so when you look at the questions later on, kalau you dapat soalan, you have to look at the question exactly, whether the question is asking you for probability of finding electron or probability of finding a hole, ataupun probability of finding the state is empty, which is hole lah, kan? So you have to read the question well, and then you have to calculate accordingly whether it's Fe or 1 minus Fe, right? So what happens? So let me just finish off with this before we stop the class. So we have discussed briefly about the thermal excitation here when you increase temperature to above 0 Kelvin. So let's recall that when T is equal to 0 Kelvin, your Fermi-Dirac distribution function is represented by a step function square, right? On the other hand, when your T is equal to T1, for example, and T1 is obviously more than 0 Kelvin, okay, katalah T is now equal to T1, where T1 is more than 0 Kelvin. So look at the plot now. Fe is on the Y, energy is on the X. So it's against the convention where you sketch your band diagram where energy is on the Y, right? Tapi you can actually flip this. You can just flip this whole curve anti-clockwise 90 degrees. Then you mirrorkan dia supaya you can get something like that. It can be done as well. You can plot E like that and Fe like that, right? Dia akan jadi just flip the thing. Okay, so if you look at this curve, for example, so that means at T more than 0 Kelvin, or when T is equal to T1, so you can see that the graph now takes this shape. Okay, it's no longer a step function. However, you can see that graph, yeah? Okay. You can see, you can see that graph, and EF is here. So sebelum ni, we can only get, we got all the electrons in the E below EF as 1. E below EF as 1. So semua electrons duduk dalam step function, the area under the curve, right? And you couldn't find anything above EF because it's just a step function and it is equal to 0 when E is more than EF. But due to the increasing temperature, you now can see that, remember energy is on the x-axis now. So kalau you nak imagine the band diagram, you have to flip the band diagram lah, right? So now you see area under the curve for this particular this particular graph, you tengok dekat sini, this area between the step function and t equals t1 is actually the area that is evacuated by the electrons. So that means electrons evacuate these particular energy states in order to be thermally excited to the above energy states. Okay, so you tengok dekat E less than EF, slightly to the left of EF, you can see that is the exact area that is being evacuated by the electrons due to the thermal excitation. And these thermally excited electrons are occupying the energy more than EF right above the EF. Okay, so can you notice the area on the curve for the left and for the right that is shaded? Do they possess the same area under the curve for the area shaded? Okay, sama kan? So that means the very same amount of number of electrons which evacuated the ground states at T more than 0 Kelvin, or T equals to T1 in this particular case, are the very same electron occupying the energy states above EF at T equals to T1. Because these particular electrons are actually excited here now. Remember, E is on the x-axis. It's not like the typical convention. So you can see non-zero probability is no longer zero of finding electrons at energy higher than EF because they are now thermally excited. Above EF will be occupied by electrons, and some energy state below EF will be empty as a result of the thermal excitation, right? So means some electrons have jumped to higher energy levels due to additional thermal energy or the thermal excitation. So now let's see what happens when you keep increasing the temperature to T equals to T2. Second condition, second line, where T2 is higher than T1. So you can say perhaps T1 is equal to, say, 150 Kelvin, where your T2 is like 300 Kelvin, perhaps. Again, it's not zero. At the point, it can be beyond 300 Kelvin, for example. Now you have these lines, this curve. And take note that, let's have a look at the same area under the curve. Sekarang dia punya areas vacated, the energy state vacated by the electrons of E less than EF are this much. And this much of electrons are now thermally excited into the upper region, the upper energy states. Right? So can you notice the areas under the curve for the left and the right, are they the same? At T equals to T2. Can you see left and right? Same, right? So same thing. The same thing repeats. So it's just that you have more and more electrons are thermally excited into higher energy states, right? So you can also notice in the center, there where the curve crosses. So what is the value of probability when E is equal to EF at any condition? You can see at T equals to 0 Kelvin, T equals to T1, T equals to T2, what is the value of Fe at EF? Half, right? So when T equals to 0 Kelvin, when T equals to T1, when T equals to T2, when T equals to T whatever, the value of Fe will always be 0.5. That's why kadang-kadang you can see the definition of Fermi energy is like the energy where the probability of finding an electron at that particular energy equals to EF is 0.5. So some definition give you like that. To be the definition of Fermi energy. Fermi energy is defined as the energy where the probability of finding an electron at that particular energy state is 0.5. Okay, so that's why you can see here it never changes, right? Whether it's at T0 Kelvin, T equals to T1, T2, T3, whatever. So it will still cross at 0.5. Okay. So this means, let's just finish it off. The Fermi energy EF is defined as Fermi Dirac statistic as the highest occupied quantum state in a system of fermions. In this case, we're talking about electrons at absolute zero temperature. This works well for metal, but EF is in the middle for the band gap of semiconductors or the forbidden energy gap. So this means that EF is in the middle of the band gap of a semiconductor. So if you're talking about a typical crystalline silicon where this is the CB, this is the VB. So if you want to write down as the energy, you can write down as EC, you can write this down as EV, you can write the whole thing as EG, the forbidden gap. So now EF lies in the middle of the band gap. Okay, EF, EG is the whole gap, but EF is in the middle of the band gap. So if you're talking about 1.12 electron volt for crystalline silicon, what is the value of EF? If you're talking about 1.12 for crystalline silicon, what is the value of EF? Anyone? It lies exactly in the middle of the band gap. So what is the value of EF? Can you do some simple math? Right? 0.56, 1.12 divided by 2, half the forbidden gap. Okay, so that means for an intrinsic silicon, undoped crystalline silicon, undoped, the story is different for dope. Sekarang kita talking about undoped, pure silicon, there's no impurities inside, just silicon, crystalline silicon to be more accurate. So the EF lies right in the middle of the band gap, which is equal to 0.56 electron volt for crystalline silicon, right? And we'll see later on when we talk about extrinsic, when you incorporate impurities or dopants into the crystalline silicon, you're going to see that the EF will change accordingly, right? We're going to see later on how does it change. So for a hint, I'm going to tell you that when you dope your semiconductor to N-type, your EF is going to move slowly towards your CB. So that means as you increase doping level, you're going to go up, closer to the CB. On the other hand, if you dope your crystalline silicon to P-type, increasing doping level, the EF is going to move closer to the VB. Okay, and eventually you can tell right away when you're given a band diagram with a position of EF, you can tell right away whether it's intrinsic or pure, or P-type or N-type, depending on the level of EF. Okay, so let's just stop here for today. Let's continue tomorrow with more information on this particular topic. Okay, so is it okay so far? So maybe it's not so clear just yet for you. So in this particular topic, we're gonna do some calculations at the end. You can see example 1, 2 at the end of this lecture note. We're going to do some calculation later on, and that will make more sense in terms of what is FE, E, EF, KT, how do you plug all those values in, and what are the results due to each particular case. Okay, so they're going to make more sense at the end of this particular topic. So if you still couldn't imagine, so let's just bear with me. You can revise, and I can guarantee you that it will make more sense when you do the calculation later on. Right? Anything? All good?
Yes, doctor.
Okay, cool. If there's no question, I'll see you tomorrow then. Bye-bye. Take care. Assalamu alaikum.
Goodbye, doctor.